All right, so let's talk about deep neural rejection. I was very pleased to get this working. Took me a whole week to get it working because the original research paper was very hard to understand. And in particular, it made it very difficult to see the effect. They had some complicated mathematical analysis to show whether it worked. And it took me a while to find a simple way to show how it works. So here's what's going on. We've talked about this. If you have um, images that have been modified to fool your model. So it's an evasion attack. You have images that have had extra dots added to them in a way to fool your model. We'd like to have a defense against that. And here's what we're going to do. We have a neural net processing through many stages from the bottom here, and then deciding what category to put things in. And then to protect the model, we're going to add 3 support vector machines over here on the side, classifiers, that try to predict the class from various representation layers of the model, and then combine them to one score. And then we're just going to throw away the ones that are outliers based on that score. And we've done this before. Remember when we had the one where you took a bunch of images and sorted them into 50 groups with k-means and found the center and applied a label to everything in that group, we eliminated the ones that were 1% outliers that weren't really on anywhere near the center of the group. In the same method here, we're going to find ones that just look funny. And this is the point. Find images that just look weird and refuse to accept those images. That's the idea. And so we'll see how good this is. So the first step, you have to install the SecML library, which is kind of slow. It takes maybe 30 seconds, so I did it in advance. And then we'll download a training set again, which is the MNIST data set that includes 70,000 handwritten images. So I've already run this. It's done all these library installed, and it's got the MNIST data downloaded. And here's the shapes. That's a typo. That should say shapes. So we have 1,000 images with 784 pixels in each image, and we have 1,000 labels. This is a labeled data set, so we can do supervised learning. So we're going to view the images as always. This is important to me so you can understand it. I want to see the images, and I want to see the effect of the attack, and I want to see the effect of the defense. So here's some of the images. See, it's showing you the first 20 images. The images here and the label is above it. So there you are, just as before, handwritten images with labels on them. This one here looks a lot like a 6, but it's really a 0, that sort of thing. All right, so now the unprotected model, we're going to make a model deep neural network and see how well it predicts these images. All right, and so here's the first 20 predictions. So the first 3 numbers show the image number, the predicted classification, and the correct classification. So this one, the image 0, it said it was a 7, it's really a 7. It looks like it's getting most of them right. I'm not sure there are any errors in the first 20 here. Image number 8, it got right. So image number 8 is really a 5, but incorrectly classified as a 6. And image number 18 was really a 3, but it incorrectly classified it as a 5. So it does have a few mistakes. And these are the weights of the output. Remember, the way the model works, it gives you a scalable output, and the largest output is what it is. So here, a 2 has an output of 532, but the 7 has an output of 5005. So it got this one right. Nothing else was even close. But this 18 that it got wrong, see, it's 5 had a score of 730, and 3 had a score of 712. So the right answer was 3, but 5 had a slightly higher score, and off it went. So you see, it was pretty close to getting it right, but it did get it wrong. All right, so now we're going to attack that model. We're going to create evasion images from the first 20 images. So take the first 20 images and modify them so the model will make more errors on them by carefully adding some dots to them that are chosen to do the maximum harm to the model by hitting areas where those dots will have the highest weights affecting the answer. So that's the CATT evasion library we've got here. which is why we had to load secml. So we got these Python functions that do exotic things like this, like examine a neural net and carefully calculate which changes in the input would have the most effect on it. So now it's done with the attack. And you see these are all poisoned images with extra dots added to them. And here's the label. So you're going to take a 7, you're going to add some junk to it, and then tell the model it's a 0. And take some 2, add some dots to it and tell it it's a 0. Add these dots and tell it it's an 8, and so on. So these are the malicious images designed to maximally confuse the model. And the lower part of this is going to show a chart of 20, and you're going to see correct and predicted. Now it gets everything wrong. This is the score on these 20 malicious images. Oh, I see. Wait a minute. I'm sorry. I got this wrong. This is not poisoning. This is evasion. So you didn't tell it it's a 0. You put these dots on a 7, and it interprets it as a 0. This is the prediction of the model. And as you can see, it's getting them all wrong. And here's a chart showing the number of successful evasions is 20. So this model is very vulnerable. Adding these little bit of dots is able to fool it. So it takes a lot of mistakes. It gets everything wrong. So now we're going to choose, they're going to add do the calculations for the protected model here. So this one is going to prepare the 3 support vector machines on the side and train it on the 1000 training set. So it learns to choose some kind of measure of the output of the model, and then train it and find out what range that measure is in, so it can define what threshold would give you 1% rejection. So it takes the training images, calculates these quantities over here on the side. We'll go back there. So we have the model here that's working, but it's vulnerable. So we add these 3 support vector machines to measure the output at different layers of the model and combine them into one number, take the whole training set and calculate them all, so we can now choose where the 1% threshold is. So we're going to throw away the outliers that are out here. So on the that's what it's doing now, training these classifiers and finding the threshold that will throw away 1% of them. All right. And then we're going to see the predictions and rejections. So it's taking time here. Is the fitting? Okay, that's interesting. If you hover over it, it shows something. All right. It's the training that's going on. Training is, of course, what takes time. It has to calculate the output of the model on all the images and then change the parameters over and over again, optimizing them. Okay, it's done. Now it's finding the threshold. Okay, so it figured out that the threshold is approximately -1 on the output signal. That's what it takes to reject 1% of the images. So let's view how this model operates on the unpoisoned images, or unevasive images, I should call it. The images that have not been modified. We're just going to see how it predicts. Remember before, it predicted 20 out of 20 correct. Here, it's getting them right, but some of them have an R. Some of these images were rejected, 2 of them. Remember the 2 it got wrong before. It got 8 and 18 wrong before. Now it rejects them as outliers, saying, these images look funny. I'm not going to use those images. It now has an option. Before, it had to sort every image into one of the 10 bins. Now, it has a 1% chance of refusing to classify this image, saying, that image looks bad. And 2 of these looked bad. All right. Also, it rejected number 15. So it rejected a few of these. So now we're going to prepare attack images for this model. So even if you let your attacker have complete knowledge of your model, including complete knowledge of your defense, it's still not going to be as successful as what we're going to see. So we're going to see the attack images and the prediction, and a -1 means it detected that that image was unacceptable and refused to classify it. And as you can see, before it got fooled 20 out of 20 times, now it frequently detects the image as malicious and refuses to classify it. So the only 6 of them were now successful at evading correct classification. So that's taken a while to do the attack here, but that's what I wanted to show you, and I was very pleased to get this working. You can see the effect. Without the defense, when you run a standard attack against the model, it has 20 successful evasions. But with the defense, the same attack only has 6 successful evasions because 14 of the images it recognizes as outliers and refuses to classify them. So that's a defense against these things, and there are various flags you can get by modifying the parameters. So I'm going to stop this recording.